The next thing that I'm going to teach you how to do is turn a carboxylic acid into an ester. This is section 17.8, and it is called Conversion of Carboxylic Acids to Esters. If we were actually having class in person, this would be something that you would do in lab. And it's a really fun lab because esters smell, and some of them smell really good. So we would be making like strawberry smells and minty smells and things like that in lab. And it would be a lot of fun. Carboxylic acids react with alcohols to make esters. And the reaction looks like this. We can take any carboxylic acid. I'm just going to draw a little tiny carboxylic acid. So this is our carboxylic acid. And remember, the characteristic of the carboxylic acid is that it has this carbon-oxygen double bond with an OH group directly attached. So that's what is making it a carboxylic acid. And we react it with any alcohol. I'm just going to say like CH3OH. So here is our alcohol. And the characteristic of the alcohol is just that it has an OH, and there isn't anything else along with it. Like it doesn't have a carbon-oxygen double bond along with it or something like that. And this reaction is going to need catalyst, but I'll fill that in after we draw the product. So we make an ester, and if you remember, the characteristic of an ester is that it has a carbon-oxygen double bond with an oxygen that has a carbon chain hanging off the end of it, not an OH. So we make an ester, and then we also make water as a byproduct of this reaction. So ester right here. And then for the catalyst for this reaction, we need an acid. The acid that we usually use for this reaction is sulfuric acid, which is H2SO4. So I'm writing it underneath the arrow, which is typically where we write the formula for a catalyst. Sometimes this reaction requires heat. So sometimes you'll see H2SO4, heat. And like you've seen a few times, there's going to be a lot of different ways that we can express the catalyst and the heat in this reaction. So sometimes instead of writing H2SO4, we might just write H+, which is our abbreviation for an acid. Or we might write H3O+, which is a slightly bigger abbreviation for an acid. And then in terms of the heat, sometimes you might see the Greek letter delta, which is just looks like a triangle, and that's our abbreviation for heat. And also, it's important to note that not all of these reactions require heat. So sometimes you won't see heat at all in this reaction. And that's okay. It's not a trick. It doesn't mean that the reaction won't work. It's just not always going to be there. Don't stress out if it's not there. So let's practice a couple of these on paper. And we're going to start with this carboxylic acid and the same alcohol. And I'm going to try to mix up as much as I can. I'm going to try to mix up what you might see on the arrow, just so you can get used to seeing it a variety of different ways. So there would be one way that somebody could write it, putting the H+ on top instead of on the bottom. And you know what I'm going to do to try to make this a little bit easier for you to visualize? I'm going to write the acid in a color, or the alcohol in a color, so we can watch the two come together. So for this reaction, when you're predicting the products of the reaction, I want you to start by drawing the carboxylic acid, everything except for that very last hydrogen. So we're drawing everything except for that last hydrogen. And then in the place of that last hydrogen, we're going to add the carbon chain of the alcohol. Just like that. Oh, I see, I intended to do it in a different color. Just like that. And we have the hydrogen that we lost from the carboxylic acid coming together with the OH from the alcohol to make our water product. So that's not too bad. This reaction is not that tricky. Let's also, while we're making these esters, let's practice naming them as well. Because naming esters is hard. So remember, when we name esters, the name has two different words in it. One part of the word is derived from the name of the carboxylic acid. So it's actually derived from the name of this carboxylic acid right here. And what is this guy's name? Well, this guy has 1, 2, 3, 4 carbons. So that makes it butanoic acid. As an ester, we're going to call it butanoate. The other part of the ester's name, which comes first, is the name of the carbon chain that's attached to the ester. Based on how many carbons are in that chain, this carbon chain has just one carbon in it, which makes it a methyl. So this ester's name is methyl butanoate. Let's try another example. So we've got this little 2-carbon carboxylic acid. Let's just name it right now. This guy's name is ethanoic acid. But this guy also goes by a common name, acetic acid. So it's like it has two names. It has a fancy name and it has a nickname. And let's react this ethanoic acid with a big alcohol, this alcohol right here. And this time for the reactants, I'm just going to go H2SO4. I honestly don't know if this particular reaction requires heat. It might not, but on paper we're going to say it doesn't. So for your product, you're going to start by drawing the carboxylic acid, everything except for that very last hydrogen. And that's all of this right here. And then you're going to add the R group from your alcohol, hanging off the end. So it's going to feel a little funny to draw it. There it is. Plus, you've also made a water molecule, a hydrogen, and an OH. And let's name this guy. So the carboxylic acid, ethanoic acid, that is going to become ethanoate. The beginning of the name of the R group, which is cyclohexyl ethanoate. These are tricky names. You could also use the common name acetic acid if you wanted to when you were naming this. So you could call it cyclohexyl acetate. That sounds a little less awkward. Let's do 2 more examples. So here is this carboxylic acid, which is a 1, 2, 3 carbon chain, which makes it propanoic acid. And we're reacting it with, let's choose a 2-carbon alcohol, like that. And what should I do for the catalyst? This time I'm going to go H2SO4 on top with the triangle, delta on the bottom. So there's another way that you might see this. So for the products, I want you to start by drawing the carboxylic acid. Draw every single thing except for that very last hydrogen. And then I want you to add the carbon chain from the alcohol, just like that. Plus, we also have water. And let's name this guy. So propanoic acid, the name of the carboxylic acid, that is propanoate when it becomes an ester. And our little carbon chain coming off of the oxygen, that's a 2-carbon chain, so that is an ethyl propanoate. And I have one more example that I'm going to show you, and this is actually a really tricky one. It's a big molecule, and this is one of the questions that you have on sapling. So this, we are going to start with salicylic acid. It's a carboxylic acid that also has an alcohol group on it. This is salicylic acid, which we have talked about a couple times. It's a beta hydroxy acid. It's the ingredient that comes out of meadowsweet that burned people's mouths. And we're going to react salicylic acid with ethanoic acid or acetic acid. And ethanoic acid or acetic acid. And what have I not done yet? I feel like I've done every single possible option here. H plus and heat. So this is a really interesting combination because with these two molecules, we have a carboxylic acid, and an alcohol. We've got a little bit of both. But this is going to be the formation of an ester. So since both of the molecules have the carboxylic acid functional group, only one of them is going to actually act as the carboxylic acid in this reaction, even though they both have it. Salicylic acid is the only molecule that has the alcohol functional group. So in this particular reaction, it has to be the alcohol because it is the only alcohol functional group between the two molecules. And then acetic acid or ethanoic acid, it has to act as the carboxylic acid then. The alcohol and the carboxylic acid can't both be on the same molecule. So this is tricky. What we're going to do, we're going to approach it the same way that we always would. We're going to draw the carboxylic acid group first, everything but the oxygen. And remember that we are using ethanoic acid as our carboxylic acid in this. And then we are going to go to salicylic acid and we are going to attach the R group, the carbon chain, which is what I just circled in red. All of that right there is going to get attached. So it's going to be kind of weird to draw it because we're going to have to be a little bit careful about how we draw it. Oops. But there it is. I've managed to get everything attached like that. And this that we just made on paper, this is aspirin. It is one of the ways that it's made is by combining salicylic acid with ethanoic acid. Aspirin's real name, technical name, is acetyl salicylic acid. So one of the questions that you have on sapling in your homework 5, and this is question 5, it is giving you the structure of salicylic aspirin and the structure of ethanoic acid, which it actually wrote out in condensed notation, CH3COOH, like that. And then it asks you to come up to draw the structure of the aspirin product. And then the last part of that question, it asks you what type of functional group was added in order to form acetyl salicylic acid. What functional group did you create? Well, in all of these reactions, the functional group that we're creating, is the ester functional group.